Okay, in the last class we have seen this, that if there is a WSS process, random process x n goes through a linear time invariant system that has impulse response h n and output is y n, then y n WSS, that is it has also mean which is independent of the index n, that is same everywhere, and its correlation depends only on the gap between the two samples, not on their absolute locations, that we have proved. In fact, we worked out the expression for output correlation or autocorrelation, you can say. It was this. Input R x x is k plus L minus R. All right. So, this finally becomes a function of k, because L, you sum over L, so L goes, you sum over R, so R goes, the right hand side is a function of k only, there is no n. As a result, output autocorrelation does not depend on the index n, it only depends on the gap k. So, it was stationary in the second order also, and already shown that stationary in the first order, that is in mean, and therefore, it is WSS. Therefore, what is output per spectral density? Because if it is WSS, I can take the DTFT, discrete time Fourier transform of output autocorrelation function, and call it output per spectral density phi y y e to the power j omega. There is nothing but this all right, and then R y y k you substitute by this expression. So, you will have triple summation. Now, you see what is the meaning of triple summation? You take some value of k, for that take one value of R, move L over the entire range, then another value of R, again move L over the entire range, and that way after you finish all values of R L, then again move k to another value, repeat the same thing. So, basically you cover a grid, 3-dimensional grid, one axis A k, one axis R, one axis L, and all points of k, L, R, this triplet. You will get the same thing if you interchange the order, that is maybe you take R first fixed array value, for that take L fixed array value and then move k over the entire range, then take L another value, again for that move k over the entire range, and then once you have finished, then again change R to another value, and then again do the same thing, and like that you will cover the same grid. It is called interchanging the order of summations. So, that is something which is always useful in our signal processing in particular. Whenever you come across double or triple summation, you have to interchange the order of summation, then only again new results come. That is what has been found. So, I keep this summation outside HR, this as it is. The k summation I send inside. Earlier k was fixed to a value one time, and then R and L were varied over the entire range, then again k another value, again R and L were varied over the entire range. You will get the same thing if you first take R equal to something, then vary, then again take L something, move k over the entire range, then again L another value, keeping the same R, k over the entire range. That way you cover all L R, and then again take another value of R, do the same thing. So, you will cover all the all the ranges of k, L, R, all the possible values of this triplet. So, that is what I do. So, inner summation is over k. So, only those who are dependent on k are inside, those who are dependent on L they are inside, those who are dependent on R they are outside, they can be pushed outside. So, k equal to 0 to k equal to minus infinity, I am very sorry. E to the power minus j omega k. And now, some simple manipulations. what I do, I write RYK as it is. Sorry, it is not RYK, I am very sorry, it is RXX K plus L minus R. So, e to the power minus j omega k. So, here again RXX K plus L minus R. Now, one thing you see, you take particular value of R. So, that is fixed now, okay, in the inner summations, and then again take another value of L, fix that. So, 1 R for that 1 L. For those chosen L and R, you take K over the entire range. Then again you vary L and then vary K, R like that. But once you choose 1 R and then 1 L, they are constant within this summation over K. So, L and R are constant, and K plus L minus R e to the power minus j omega k. So, what I can do, I can make it K plus, here I have j omega k only, so I can make it K plus L minus R. To cancel out these extra terms I have brought in e to the power minus j omega L. So, I must have e to the power j omega L, okay, and that depends only on L, not on K. So, it can come outside this summation as a common, goes outside the summation here, and I brought it e to the power minus j omega minus R. So, e to the power plus j omega R, I have to cancel it by e to the power minus j omega R. That will go out as a common, again that depends only on R. So, that will again go out as a common of this summation. So, it will come here, all right. You can call this as M. So, this index is M. L and R are fixed. So, as k is minus infinity, M goes to minus infinity. As k goes to plus infinity, M goes to plus infinity. So, Rxx M e to the power minus j omega M, summation over M. So, this is the discrete time Fourier transform of autocorrelation function Rxx M, which is the power spectral density of the input, right, phi xx e to the power j omega. So, this entire quantity is phi xx e to the power j omega, this summation. And now, this does not depend on L and R. So, this will go outside, and this summation. So, what I am left with, I am writing here this phi xx e to the power j omega, it has already gone out. Then you have got H R e to the power minus j omega R. For each R, you put the value and then run L over this summation. H star L e to the power j omega L. But that you can write as, see this product H star L e to the power j omega L, it is as good as H L e to the power minus j omega L, and then whole is conjugated, H L and then summation. Let me explain again. If I take the conjugate out, so I should make it e to the power minus j omega L, then again conjugate out. So, H L e to the power minus j omega L whole together conjugate and summation, but summation of conjugate is conjugate of the summation, okay, conjugate of the summation. So, this is this summation and then the conjugate, okay. See, I take star out, and from this I make it, here I make it to the power minus j omega L, so a star goes out again, okay, because conjugate of e to the power j omega L is e to the power minus j omega L. So, e to the power minus j omega L, then star makes it e to the power plus j omega L. So, I have H L e to the power minus j omega L product star and then summation. So, summation of conjugated quantities is first you sum and then conjugate, that is Z1 star plus Z2 star is Z1 plus Z2 then star, Z1 plus Z2, here I have infinite sum. So, Z1 plus Z2 plus Z3 and dot dot dot, first that then star. So, this is nothing but the transfer function h e to the power j omega, discrete time Fourier transform of HL or HN, whatever be the index you choose, h e to the power j omega and then a star, and that goes out as a common, and this again you are left with another h e to the power j omega. So, what you get is phi x x e to the power j omega, then h e to the power j omega, and then h star e to the power j omega. Okay, h to the power j omega star, so h star e to the power j omega goes out as a common, then h to the power j omega, which is mod since it is mod, even though h to the power j omega is complex for every omega, when you take mod and square, this is real and this is already real, and that shows output per spectral density satisfies the condition that it should be real. This is a very important result. Important result because you can design a filter with a specific transfer function, frequency response, so that even if input per spectral density has a particular shape, like high here, low here for certain frequency and all that, you can alter that by designing the filter. So, you can give good gain, high gain to some zone in frequency and low gain in some zone, other zone of frequency, that will make it band pass, band reject kind of filter, and output per spectral density can be shaped. Its shape can be determined by your design of a filter. Okay. So, because remember only the magnitude response comes. So, you can design a filter with a low pass characteristics, that is only up to some frequency its value is high, otherwise 0, close to 0. So, input per spectral density only in the pass band will be amplified, otherwise gone. So, it will be a low pass random process. Okay. Low pass random process means not its individual discrete time Fourier transform of a particular yn, but in a statistical sense you take the autocorrelation, then DTFT, that is power spectral density, okay, and that will be like this low pass signal, because if you integrate the power spectral density from minus pi to pi, we have seen already, it will give you the average power. Now, if it is low pass signal, it will mean that average power is located only certain low pass band and nowhere else, and likewise so on and so forth. Okay. This is a product relation, that is why even if this power spectral density is actually multiplied by this mod square of transfer function or frequency response, because it is product. If it is high, overall will be high, if it is low, overall will be low. That way you can give a shape, you can adjust the shape of the output per spectral density. All right. Okay. A particular case, suppose, what is it? Suppose input is such R x x k, it is 1 if k equal to 0 and 0 otherwise. All right. That means R x x k is delta k. We know delta k is 1 when k equal to 0, 0 otherwise. What does it mean? It means that when k is 0, then only there is correlation, that is variance. Variance is this much. But for any k, gap of 1, k is 1, gap of 2, k is 2, gap of minus 1, for any gap, the correlation is 0, which means every two different samples, whether they are immediate neighbors or far away neighbors, they are uncorrelated. Okay. In that case, R x s k is delta k, and then your for these processes is but R x s k is delta k. If you put delta k, only k equal to 0 case is to be taken, otherwise 0, and e to the power 0 is 1. So, you get 1. Okay. If R x s k is not 1, but maybe some constant n, then it will be and here it will be n. That is, part spectral density it is constant n from minus pi to plus pi. This is called White process. This random process is called White process, because all frequencies from minus pi to pi are equally present, like white light, White process. So, if that LTI system Xn which is white, then Yn its part spectral density will be as it is mod h to the power j omega whole square input part spectral density, right, that we have proved in the previous page, which is, but this is equal to capital N. So, in this case it does not depend on input. Just by designing the filter you can give a shape, because only mod h to the power j omega whole square comes as a function of frequency, other factor is a constant independent of frequency. So, for white input you can just design the filter and thereby make the sequence as a random process, that is low pass or high pass or band pass, meaning part spectral density is low pass type or band pass type or high pass type, like that. All right. So, that much for part spectral density now, but now one thing I left out, I said that I will show that this function is actually non-negative. Okay. There is this part spectral density is non-negative. So, suppose this is your part spectral density. This is a point omega, and you have to show that phi xx e to the power j omega, you can call it omega naught is greater than or equal to 0, real and already seen. So, it is greater than or equal to 0, and for any omega naught, that will mean that is always above 0 or equal to 0, so it is non-negative. So, omega 0 is given. What I do, I take a small segment of width delta omega. I have this random process Xn whose part spectral density is this, pass it through a band pass filter h e to the power j omega, which has just value 1 and center point is this omega naught, and this width is delta omega. This is pi minus pi, and if I pass it through this, output Yn phi yi e to the power j omega will be input part spectral density times now mod h to the power j omega square means it will be 1 square is 1 within this range, otherwise 0. So, therefore, output power will be, what is, how will this look like, phi y e to the power j omega, only at omega naught it will be taking this kind of shape. Omega naught, this kind, otherwise 0. Okay. You can, for the time being, you can assume this to be a rectangle, because delta omega is so small, this width delta omega is so small that the function hardly changes. So, it is approximately a rectangle. So, you have to just take the integral of these. What is r y y 0? It is 1 by 2 pi integral, this we have seen earlier, phi y e to the power j omega d omega, right. But phi y e to the power j omega d omega integral means the area under the curve. Now, area under this curve is only this much. Okay, and if it is a rectangle, the area will be 1 by 2 pi. Height is, because it is coming from phi x x, okay, you are multiplying phi x x e to the power j omega at the point omega naught, and at omega naught its value is phi e to the power j omega naught, and you assume this value does not change because this delta omega is so small, the function hardly changes. So, height is phi e to the power j omega naught, here phi e to the power j omega naught, it is height. This is phi x x e to the power j omega naught, because you are multiplying phi x x e to the power j omega by this mod square of the transfer function. So, elsewhere it is 0, only within this band its value will be mod square of this is 1, because height is 1. Okay. So, you are multiplying this by 1 at frequency omega naught and around that for a strip, for a very small slot of delta omega, infinitely small. So, value of this function at omega naught is phi x x to the power j omega naught, and it remains constant. I am assuming it is a rectangle. So, area will be this value phi x x to the power j omega naught times this width. So, it will be phi x x e to the power j omega naught into the width. Only that much is the area. But this r y y 0, we know r y y 0 is the power, average power, it can never be negative. So, this. Now, here right hand side 2 pi is positive, delta omega positive means this is non-negative, isn't it? So, this shows phi x x e to the power j omega naught greater than or equal to 0, and omega naught we chose arbitrarily. So, this is true for all omega. Okay. So, this is for power spectral density. Estimation of power spectral density from random process data is a very big topic. It is called spectral estimation, power spectral estimation. There are various approaches, just order spectral estimation, and many important signals are kind of analyzed spectrally. Most important of them is speech. A lot of research has gone into speech spectral analysis over decades and still going on. But I will not get into this because this is not a course on spectral estimation. These just come along with this adaptive signal processing. Sometimes we need, so that is why we build it up. All right. So, with this background of random, probability density, joint probability density, conditional probability density, statistical independence, multiple random variables, correlation matrices, covariance matrices, both for real and complex random variables, and then some matrix operations like Hermitian transposition, and properties of matrices called Hermitian matrices, all important properties, including a special case of Hermitian matrix called positive definite matrices and its properties, and then these random processes, in particular White-Sand stationary random processes, action of linear time invariant system on a WSS input, what do you get at the output, that is also WSS, what is the output power spectral density in terms of input power spectral density, all these things we covered. With this background, we will now go to the next topic, which is basically one step towards adaptive filter, and that is called optimal filter. All right. So, that I will do in the next class. Optimal filter. Optimal filter is halfway through. By this, actually, we try to estimate some unknown sequence from a given sequence just by some filtering of that, FIR filtering of that. So, we derive kind of optimal filter, which will give a filter output the best estimate for that unknown sequence, and then that will require knowledge of some statistical properties of or data of the input and that unknown thing, which if not known will have to be learned, will have to be adjusted from data only. That brings us to training or adaptation, where the filter will be learning itself and adjusting itself by learning from the incoming data, and that will make it an adaptive system, and in our case adaptive filter. So, That I don't want to start now because not much time is left. So, we will begin that, we will start with that in the next class. Thank you very much.